And my name is Theron Tobalski. I'm the Assistant Executive Director with the Illinois Ready Mix Concrete Association. Part of my job is to work with the engineering community to understand all different types of concrete topics. For today's webinar, we will be following the antitrust statement of the Illinois Ready Mix Concrete Association. That is posted on our website for each of the different webinars that are listed on our website. If at any point that you feel we are violating any antitrust rules, we encourage you to jump off the webinar, and we hope that doesn't happen. So this webinar will be recorded, as all webinars are. They then are posted on the Illinois Ready Mix Concrete website at www.irmca.org. We'd like to take a look at today's sponsors. All these companies have sponsored today's webinar. If you go to today's webinar page on the NRMCA website, these companies have also put links to different information that they would like you to read. With that, the next slide. Today's presenters, we have two great presenters today. We have Don Clem, who's a PE who lives in Colorado. He's the Vice President, Local Paving for the National Ready Mix Concrete Association. And we also have Jonathan Pease. He is the CEO and founder of Rock Solid Stabilization and Reclamation. And with that, I hope everyone enjoys the webinar today. I'm going to turn it over to Don Clem.
Great. Thank you, Theron. So I'm coming to you from beautiful Denver, Colorado today, and Jonathan is out in Utah, I believe, and we're going to hit 100 degrees here today. So I wish I was back in Illinois. I understand the temperature was a little bit more moderate back there. Just a little bit about the National Ready Mix Concrete Association. We are a trade association. Established in 1930, we represent about 75% of the concrete production throughout the United States. And if you want to learn more about us, you can look on our website. We have a couple websites, product oriented, paveahead.com, which is focused on pavements, and we have the Build with Strength .com website, and that focus of that is concrete building sustainability. So I would invite you to check out those sites. Our speakers today, myself and Jonathan, just a little bit about us. I've spent most of my career out in the Rocky Mountains. I do cover the northwest part of the country. I've got about 41 years in practice, both as a civil engineer and then quite a few years in the cement and concrete industry. My focus areas have been pavement design, concrete overlays, and forensics, troubleshooting primarily. And we're fortunate to have Jonathan Pease with us today. It's always good to have a contractor as a co-presenter, because they face the reality of building what us engineers come up with on paper, which sometimes can be a little bit difficult. He's CEO and founder of Rock Solid Stabilization and Reclamation. They're one of the largest reclamation companies in the country. He has over 30 years experience in infrastructure construction. And he's a very busy man. I mentioned he's in Utah. He's traveled a lot. He's the current president of the Asphalt Recycling and Reclamation Association, which is the kind of the main recycling association, if you will. They write a lot of specifications. It's a very, very good group that he is the volunteer president of right now. This is what our local paving team looks like. And you can see we each have assigned territories. As I mentioned, I'm based out of Colorado, and I cover the Rocky Mountain Northwest. Luke Mahue, who's currently on vacation, actually has the state of Illinois in his territory. He's in this orange territory. And each of these people bring different expertise to the team, and we do cross boundaries quite a bit depending on what a project need might be. And we work under the direction of Brian Killingsworth, who's a very good paving engineer. He has a master's of paving from Texas A&M and is a wealth of information. He's our team leader. This is our disclaimer statement that we put up in every presentation that we provide. Basically, it says we at NRMCA strive to present information as accurately as possible. We intend for you to use the information at your own discretion, and we do disclaim responsibility for how the information is actually applied. There will be one professional development hour certificate for each attendee today. Our learning objectives are to understand the definition of soil cement, full depth reclamation, learn the advantages of soil cement and FDR for rehab work for pavements, understand the process to determine the appropriate cement content target, learn about the soil cement FDR construction process, and then finally learn about the use of cement slurry delivered in a ready mix concrete truck. Our references include the Guide to Full Depth Reclamation, fondly known as FDR, with cement, and also Cement Stabilized Subgrade Soils. Both of these publications are produced by the National Concrete Pavement Technology Center. They do a very good job of producing publications. They're easy to read, very well organized. And you can find those online either at our paveahead.com site, or you can go on the National Concrete Pavement Technology Center site to download these publications. And we're also used as a reference an article that we put together last year, written by Wayne Adaska. He's a former PCA employee, Greg Halstead, who is a current PCA employee, and myself. We wrote this article last fall for the Illinois Ready Mix Concrete Association. It was published in their newsletter, and I'm sure Theron can get that to anybody that would like to have that resource. And I should mention Greg Halstead with the Portland Cement Association. He's based in Bellingham, Washington, and he is a very, very good resource for anything as far as geotechnical applications of cement and soils, be it soil cement, full depth recycling, cellular concrete. He's an expert in all of those areas. So our first topic today is understanding the definitions of soil cement and full depth reclamation. And for that, I'm going to turn control of the webinar over to Jonathan.
Yeah, if I could talk here, I get a little tongue twisted.
We got you.
I want to thank you for the introduction. I do have my camera off. I'm nothing to look at, I can tell you that. So, and I've also got bad lighting, and I'm on a laptop, so it's not the best backdrop. So hopefully everybody can hear me good. And again, Jonathan Pease with Rock Solid Stabilization, and also the current president of ERA. Oops, that first slide, I don't know if we went through that whole thing yet, but so obviously here's a slide on the different, the cement ratios and water content ratios of the different types of uses of cement. And you can see full depth reclamation and also cement stabilized subgrades are in that bottom left-hand corner, and also cement treated bases. Those are all things that are covered within the ERA disciplines, and also ERA manuals and specifications that we write, with the FHWA, and the BARM manual, which many of you may have the BARM manual, which is available through ERA. All of these, the processes are in that manual. And, those are all stuff that we work on as an organization to develop the best practices and specifications around utilizing these materials. Next. So there are some differences between modification and stabilization, and on the ERA website, you can, see those definitions in greater detail. But to me, the two basic ones are, like if you're just modifying, like, modifying and stabilization for all practical purposes, when you see them in the field, they're pretty much the exact same process. Modification usually is you're either trying to chemically modify the soil to have different characteristics, or you're trying to tackle like wet conditions and just, obviously get a better subgrade and, obviously pass a proof roll. Stabilization is more of a predetermined amount of something because we're trying to achieve a certain strength. So there's usually a mix design associated with it. Does not mean there wouldn't be a mix design with modification, because there are times that is also true. But generally speaking, and then stabilization pretty much will always have a mix design. Now, there are some generalities, and once you just do them enough, you kind of know you need 5% cement, so you just use 5% cement. But typically, you're going for some desired strength or certain, like, desirability in the end. And then you can kind of see to that, like, chart over to the right there of where you would normally see those, usually see those layers. Next. Here's a nice chart from this, also from the era and the barn manual and stuff like that, on the roadresources.org site. Just a general use of the different normal stabilizers that you will see out there. There are some other liquid and or powder stabilizers that are like polymers and enzymes and things of that nature. But these are your typical proven, been around the block for decades and decades. And it just shows you the different soils that they work in, fine grade, coarse grain, and where they typically work the best. So you got your Portland cement, and you also got your Class C fly ash, which is becoming harder and harder to get your hands on anyways. Very similar characteristics versus your lime and also your kiln dust, and then also you also have some bituminous ones that you can use in certain types of soil conditions too. So just a nice chart for reference in the future. So soil cement definitions. So soil cement refers to a compacted engineered mix of soil cement and water designed and constructed for various pavement and geotechnical applications and characteristics. And, the term soil cement can be it's an umbrella term to cover 4 types of cement treated projects. So, like a CMS, a cement modified soil, a cement, a CSS, cement stabilized subgrade. There's all these different acronyms that are used, throughout. FDR is a big one. CTB is another big one. If you're treating aggregates, a lot of times your aggregates don't have the best characteristics, so you can treat aggregates. They do a lot of that up in North Dakota, actually, where they got really sandy, non-angular gravel, and they improve the gravel characteristics with cement to make it a better quality gravel. Obviously, FDR, obviously using cement with FDR, and we're going to talk about some other additives, like in that realm later on here. FDR definition: it's the method of flexible pavement reconstruction. So this is just an HMA, not in concrete, of the existing asphalt base and or subgrade. So you're removing the existing whole entire asphalt cross section, usually into the existing aggregate base and or into the subgrade at times too, and making a nice homogeneous blend of all that and mixing it together and making that your new sub-base material, and usually to some design type strength or performance requirement that you're looking for. So it's taking that whole, and you're removing all the imperfections in that cross section and making it a better overall platform to build a actual pavement cross section on top of thereafter. So and there are, in FDR, there are like 3 main types of FDR stabilization. The first one is mechanical, which, there's a lot of states that are doing this right now. Like a lot of this is happening up in, say, Michigan, where they just don't have the budget to repave roads. So they're taking old paved roads and turning them back into gravel roads. That's basically a mechanical stabilization, where you're just taking that existing asphalt, pulverizing it down to like 1.5 inches minus. And then there's a bituminous stabilization with asphalts, emulsions, or foamed asphalt. And then there's also chemical stabilization, which is usually some type of a self-cementing type material. The biggest product for that's used for FDR by far is Portland cement. It's just readily available everywhere. It's consistent. It has ASTM and different types of specs that everybody has to make it to. It's very consistent, and it's used worldwide. And there are some other polymers and enzymes and stuff like that. And in the event that your existing cross-section doesn't have the right gradation that you need in any of these processes, you can do what the general term in the industry is add rock. You could add fines or coarse aggregates to change the matrix of your blend after you actually run it through the, actually run it through the reclaimer. So that's the, like the term add rock, but it could be fines also too. It does not have to be just rock. So it's just to get a better matrix overall. And so, here's some, like the different layers where you can see, like the cement being used in, obviously get your untreated subgrade at some point in time. You're not going to go down indefinitely. Then you could have your treated subgrade with cement. You could put cement in your base courses. You can put cement in your FDRs. I mean, it could be in your finished surface layers. I mean, it could be used throughout the entire cross section of a road. And, so it's a very versatile product for sure. So, and the soil cement family, I think we kind of did this one already, but we got cement modified soil again. We got cement stabilized subgrade, cement treated base, and FDR. So, and there's the, like the different acronyms there, which is they're obviously be used frequently in the industry, and we're just trying to create common terms. So when we're talking about them, everybody's talking about the same thing. But that's pretty difficult to get that commonality because even machines have 15 different names for the same machine out there. And I think now it's Don taking over.
Yep. Make sure I'm unmuted. Thanks, Jonathan. So next we'll talk about the advantages of soil cement in the FDR process. And I shut my camera off, so I've got a little bit better bandwidth. I think things move a little bit quicker with my internet. So there are quite a few advantages of this process for an agency or for a DOT. And you can see here, the biggest one is you're using these in-place materials. So there's little or no material that you have to haul off or dispose of. And that basically does a couple things. One is it conserves virgin material. So you're not using new aggregate, you're reusing material that a DOT or an agency has already paid for. So it's a very sustainable process because what's better as far as sustainability than recycling or reusing a material in place? You don't have to move it anywhere. So you save the energy that you would have to expend if you had to remove and replace material. You've got to haul the existing material off and haul new material in. There's a lot of emissions that are associated with the vehicles that would be necessary to do that. And the bottom line is, as Jonathan mentioned, it saves you money by using that in-place material because you're recycling, reclaiming those in-place materials to create a new solid base for either an asphalt or concrete pavement or perhaps a chip seal pavement. And you're just going to save a heck of a lot of money over removal and replacement. So the taxpayers really win with this process. And this is an era slide that Jonathan provided to us. And you can see there's just a lot of benefits that FDR has over the overlay process, and quite a few over remove and replace. And probably the biggest one is that lower cost. But the sustainability aspect is going to become more and more important. As I mentioned earlier, I cover the Northwest. I don't cover California, but I do cover Oregon and Washington. And I'm watching legislation out there every year that more and more covers construction materials. So sustainability, whether we like it or not, is going to become a bigger and bigger part of material selection on projects in the future. And in this case, it actually makes a lot of sense because it saves you money as well. So the FDR leaves a significant smaller carbon footprint compared to traditional reconstruction methods. And by using these cold processes, reusing the existing materials, working right on site, no hauling off of materials, generally speaking. We decrease the greenhouse gas emissions and conserve energy associated with that project. This is probably, beside the cost aspect, this is probably the biggest benefit I see to the overall FDR process, and that's just the performance of these subbases, particularly underneath flexible pavements. And as most of you on this call know, with a flexible pavement, you have a layered system, and the layers beneath that flexible asphalt really have a lot to do with the load carrying capacity of that roadway. And you can see that the stresses on a normal subgrade, the maximum deflection is actually fairly far below into that subgrade course. Whereas if you have a stiff subgrade after FDR, and basically after FDR, you more or less have an equivalent to a cement treated base in all reality. You can see that that maximum deflection on your roadway is much improved. And that's going to provide definitely going to provide a longer service life for that asphalt roadway, for that flexible system. So there's a lot of advantages for using Portland cement as a stabilizer. Jonathan mentioned that there's quite a few different stabilizers out there. Portland cement is known in the industry as the universal stabilizer because it works with so many different soil classifications. But the benefits include spreading the load, as we just looked at in that graphic, which eliminates the rutting below the surface. It reduces moisture susceptibility, reduces fatigue cracking in the asphalt surface, and it could allow for a thinner pavement section. And what I recommend to engineers is they don't reduce the asphalt pavement section, but rather leave it as is and enjoy a longer pavement life. I think that's the better way to go, because that will certainly increase your life cycle cost or reduce the life cycle cost on a project. So within the cement family, we've got a choice of using either a dry spreading method or a slurry method. And so there are some advantages to the cement slurry application method. And probably the biggest advantage is going to be that it reduces the dusting associated with the dry spreading method. So this would come into play in an urban setting, or perhaps you're next to a hospital or other facility where you really don't want any dusting. That would be an ideal place to use a slurry method. Also in, let's say, a cul-de-sac or very tight quarters, the ready mix truck can bring that slurry in those very tight places with ease. There is a variety of equipment available for delivering that slurry using a ready mix truck, and there's also tanker trucks as well that can deliver slurries. Laboratory has demonstrated that there really is not much difference at all between the slurry process as far as the compressive strength, unconfined compressive strength, that of a dry spreading process. So as far as performance between the slurry method and the dry method, there's really no measurable difference between those two. And here you can see results of a study. This is actually an older study done in 2009. It was done by the Texas Transportation Institute. And here's some of the findings. As I mentioned, there's no difference in the strength results. Slurry age had no impact on soil strength up to a period of 2 hours. Increasing the delay time did negatively impact the uncompressive strength for both dry and slurry. And the percentage of solids in the slurry should be selected based on the delivery equipment. And for high PI soils, 50% solids produce the best strength results in this particular study that the Texas Transportation Institute provided. We do have Illinois Department of Transportation recently adopted a special provision. We worked with the Illinois Department of Transportation along with Portland Cement Association, Illinois Ready Mix Concrete Association on preparing this specification. It was very well vetted. It was a consensus specification. And I'd like to recognize Theron Tobolsky with IRMCA and also James Kristolovich with Illinois DOT for their work. They did a lot of work on this, and it took quite a bit of time. It's a very good document, though, that was a result of this work. And I'm not going to go into detail, but what you can find is here, of course, a gradation for the pulverized material, specification on the reclaimer itself, process, specification on the slurry process with some limits, a minimum 60% dry solids content by weight is in the specification, and a time frame of 90 minutes after first contact. The material needs to be applied to the surface. So it's a very comprehensive specification if you'd like to go online and look at that. Next topic that I'd like to cover is how to determine the appropriate cement content. And we're going to focus on FDR for the sake of time, but the same provisions really apply for soil cement and the other family of cement products that you saw earlier. And the basic process is you conduct a field evaluation to determine the materials that are going to make up the existing pavement. So we want to take those materials from the field, bring them back to the lab, and combine them in that same proportion that you find them in the field. And you can obtain a representative sample with a core rig or jackhammer for the asphalt, auger or post hole digger for the base below. And then materials are taken back to the lab and recombined. It is crucial for you to obtain a good sample of all those materials and that they be combined in the same proportion that you're gonna find them in the field. And you want to take enough cores to make sure you have a representative sample for that whole project along the length of that project. And in the lab, they're going to run sieve analysis, compaction requirements, maximum dry density, optimal moisture content. And finally, they'll analyze all of the above, and the lab's going to determine the target cement content, which will provide the specified uncombined compressive strength for the project. Typically, we will see those uncombined compressive strengths in the range of 300 to 400 PSI. And one point I want to make is that more cement is not necessarily better. So keep that in mind. We're looking for a balanced design. And when I mention balance, we really want to be in this target level, right in this area. If we're below this percentage of cement target area, you can see our performance drops off. If we're below the optimal cement content target, what we find is we don't have enough strength in that base below the particularly a flexible pavement in order to provide for the load carrying capacity. So we want a good stiff subgrade. However, we don't want to get over in this area where we're gaining too much strength. You know, maybe we're up at 600 or 700 PSI, for instance, if we get into that area, then we may have a problem with drying shrinkage cracking of that base course layer, which can reflect up into the surface layer, the asphalt layer. So we really want a balanced design. We want to be in this area where we have the best performance of our subgrade material and surface course. I guess I would say the best performance of the system itself. At the end of the day, that's what is most important. We did put together a chart at two different densities, and you can see here we've got two densities of the dry soil. We've got percent cement by dry weight of material over here, and typically you'll see anywhere from 3 to 5% on most FDR projects. There's some states, Idaho, for instance, that actually uses 2%, but they have a process called CRABS, C-R-A-B-S, and when they do reclamation, generally speaking, the highway department on state highways, they don't take any of the subgrade materials below the asphalt and the base. So they stay in the granular materials, and they just use a flat 2% to stabilize those materials, and they found that that works very well. But in the normal situation, you're generally going into the subgrade material, so you're probably going to be in this range here. And then we'll look at this in a little bit more detail a little bit later. I would like to mention that Jonathan's company has put together a very nice tool which allows you to skip that chart altogether, and you can see this tool here. It's actually an app where if you put in the spread rate, truck tonnage, and width, or actually, I'm sorry, you put in the dry density, depth, and the application rate, what you can end up with is the spread rate, the coverage area, and for a given width, let's say 16 foot in this particular instance, we know we want to go 34 feet to cover that area with the cement that we're spreading. And we'll look at those calculations in a little bit more detail. But to download this, just Google rock solid stabilization and reclamation, and this particular tool will come up. And I checked it out. It's really put together well. And with that, I'm going to turn control back over to Jonathan to talk about the soil cement FDR construction process. Jonathan, all yours.
Thank you. Yeah, and if you go into the chat box, the first set of chat in there is for me to everybody, and the links for the app store for the iPhone and or Android app stores are actually there. You can just click on the links and you can download the app. It's free, and it's there for use. So and it's a very easy tool, and gets rid of the fat fingering, so and you can see everything right there. So anyways, I got to get back onto this here. So I did write down some notes that I'll hit on here in a little bit, that I did want to add either from Mike's stuff earlier, and then something else I was going to say from obviously Don's presentation. So we'll focus on the construction for FDR project for sake of time, but now a construction project is very, so if you're to watch soil stabilization and FDR, for the most part, unless you saw the difference in the materials we're blending, it's pretty much the exact same process. So we're going to go just through what it looks like for FDR, but if you're to see soil cement or CTB or something like that, it'd be pretty much the same thing there. And I see somebody just said that they can't see the like the link, so I'll have to see if we can figure out on that. And so the FDR process, you got your existing road to the left there, and it's got the existing asphalt, gravel, subgrade. Then you typically go through and you do a pre-pulverization, and you blend in that, so if you're going to do a 12-inch FDR, you want to do a 12-inch pre-pulverized typically. The only time that we have not done that, we were doing a job for FHWA where it was a 7-inch, and we did a 7-inch mix design, and the the cement content came back extremely high. So when you start seeing materials being used at higher rates than they should be used at, there's probably something goofy going on, or it's not the only best material to use, which I will bounce back quick. When we were talking about the different things out there in cement and limes and things like that, we have done quite a few projects now where we had to use like a lime first to chemically modify the soil, but then we had to use a cement to actually stabilize the soil and give long-term strength. So blends are a thing out there. They work fantastic. We're actually challenging people in Shreveport, Louisiana with this. They're just used to the way they do things down there with lime. We're introducing lime cement blends and they're kind of like, what the hell are you guys doing? And we're proving it in the field, proving it with mixed designs. And now the entire project's going that way. So there are a lot of things that are regionally people just do, and that's just what it's always been. So that's what they always do. But, you know, but there are ways to do that stuff. And then after the pre-pulverization, if you have some grade restrictions that you have to adhere to, then you can remove some excess material, and or it could be pre-milled ahead of time too with a mill before you did the pre-pulverizing. It just depends on the job conditions. Oh, and I was saying about the FHWA job too. That particular job, there was enough aggregate below the 7 inches. So we ended up doing a mixed design based on a 12-inch pre-pulverization, but still a 7-inch treatment, and just and then a 7-inch pre-pulverization with a 7-inch treatment. And the cement content was almost reduced in half, just purely from the fact that we brought some of those fines from the aggregate up into that blend, because the asphalt alone, because it was like basically exactly 7 inches of asphalt out there. So when we pre-pulverized it, there wasn't enough fines in there. So it took so much extra cement to create that fines that it needed. And it was so expensive to do. And then just by doing a pre-pulverization at a different depth than what the actual process was going to be at, had fantastic results. And that was all, you know, like an FHWA project. So, and then you do your, you know, obviously stabilize, obviously with cement, and then reshape, compact, and then you know, get all that graded and done. So your right cross-section profile, then you put your new surface on there. That's just a high-level process there of what happens. So here's some pictures. You know, you got your initial pulverization. Now we do have some older pictures in here because we want you to see that this stuff isn't new and it's been around and it's been done for years. I mean, that's an old reclaimer right there. So, you know, you'd be hard pressed to see one like that working anymore today. Here's just a good representation of what's happening inside that drum. You know, it's moving obviously to the right side of the screen. You can see operating direction there. So it's doing an upcut method. And, you know, so a lot of the drums have hydraulic rams on them that, you know, to keep them down. So the front part of your skirt and stuff like that kind of becomes you know, pressure against the asphalt to keep it from slabbing up on you so you can get your gradation. But you have to take into account speed and your drum door openings to be able to get, you know, the best gradation possible. And, you know, so this, you know, and then, you know, like you see in the top here, there's water injection bars on pretty much all the major manufacturers of reclaimers, all have similar technology. And you can see where it's getting through that asphalt down into the granular material and giving one homogeneous blend out the back of the reclaimer. So, you know, and that's what you would be seeing as you're, you know, if you're looking inside that drum, but it would be pretty harmful to do that while it's moving. So, so we have to do it with pictures. And then after you pre-pulverize, you want to shape it, and you want to shape to the grades of your final surface that you're going for, so you have a uniform cut on the mixing part. So after you spread the material, so before you spread the material for the stabilizer, you want to make sure your cross section is what you want it to look like in the end, so you're not cutting and filling your stabilized material. So obviously pre-shaping and also pre-compacting is very important to do. And then you want to apply your slurry. And, you know, and that gets done. There's obviously various methods, and we're going to talk about that a little bit later on here too, but this is just one of the methods of spreading slurry. And if you are doing a dry powder application, there's various looks of spreaders. This just happens to be one of our spreaders that we actually bought from Lafarge back in the day. And it's an old converted belly dump, you know, but every spreader you will see out there is a computerized, monitored system that, will adjust itself with the speed. Every load gets laid out, hence that's why we use that app. So if we're doing a road that's 22 feet wide and a load comes in at 26.98 ton, and we know we're supposed to put down 52 pounds a square yard, it can tell our operator exactly how far to go with that load. We lay it out and we make sure that load fits into that box, because there's humidity, or fits in the box that's laid on the ground, but there's aspects of humidity, temperature, things like that affect how the materials will flow out of the box, out of the machine onto the ground. So it's not like you can just make one simple pass and it's perfect every time. So you have to trust some old school technologies of still put it where it belongs, and visually look at it. And there's like a bunch of manufacturers of this equipment. A lot of people have some proprietary stuff that they do, and but there are parts of the country still that you will find people down south mostly that will bring a pneumatic tanker out and have somebody walk alongside the truck and get underneath it almost, and open and close valves and literally blow the material on the ground, and they have zero control over what and how much goes on the ground. And if that happens, or if you don't have specs that don't allow that, you should have something that does not allow that, because it's such crude methods that it shouldn't even be allowed anywhere in the world, in my opinion. So this is just an example of a dry spreader. And then, you got the blending of the materials. So once, your stabilizer's on the ground, whether it's in a slurry or a powder form, you got to blend it. So you got the reclaimer there. Typically you need to be adding moisture, or, not always, but if you need to add moisture, then you're going to usually be pushing a water truck in front of the reclaimer. And then that way, you get exactly the moisture content you want, because it is a water cement ratio. It is a recipe, and you got to follow the recipe in the field. And that's exactly what you can do with the right equipment. And then here's a little video on just some blending of some slurry, and like, you don't see a water truck here, but if there's enough existing moisture in the ground, along with the additional moisture from the slurry, you might not need to add water. But as you can see there, in this particular case, it likely was not necessary. So, and it's a pretty smooth operation. You could see, like, even right behind the reclaimer, if one of those cars driving by had to get into that driveway right next door, they could cross pretty much right over it. And if not right then, they could do it after like the first one or two passes with the compactor. So your disruption to, the public and getting access in and out of, driveways or parking lots, things of that nature, like adjacent roads is pretty minimal with obviously FDR. If that was a full depth removal and replace, and you got a 18-inch drop off, I don't care if you got a Humvee, you're not driving through there until somebody puts in some temp aggregate to drive through. So, or else ramps it and things of that nature. So very, very friendly for the environment of the, like of the public, and very conducive to that. Then here's just another shot of, some slurry being mixed in. This is actually up in Montana, getting mixed in with some slurry on the ground. And then you got your initial compaction, which is typically with FDR is going to be and/or soils, CTBs. Typically, you're going to see a pad foot compactor, preferably with a knockdown blade, so you can, roughly back drag and keep that platform that the compaction is happening on uniform, so you don't have a big hump. Because that, if you got a hump in that soil or aggregate, and you got a 7 or 8 foot wide drum, but you got a like 4 foot wide knob in the center, you're only getting compaction in that center 4 foot. You're not getting on your outside edges. So, and that's typically, especially for the deeper depths. If you're doing shallow or FDR at, like, say 6 inches, all in aggregate, you probably just get by with a base roller, a smooth drum type roller too, for your initial compaction. And then you have your grading, obviously there again, you want, everything to be graded back to its proposed elevations, cross slopes, and the grading process. So, like, from one to, as soon as the powder or the material gets blended into the ground, obviously if you're working with a slurry, you can't let it sit on the ground for 3 hours. A powder, you can let it sit on the ground for 3 hours if it's not, soaking up moisture. And then, but from once you get the mixing started and done to the, final grading and rolling, in my opinion, it should be closer to that 2 hour mark. Some specs are like 4 hours, But the tighter you can keep that, if you can get it done in a half hour, you're going to have a better product than if you get it done in an hour and a half. And an hour and a half should be better than if you get it done in 3 hours. So the tighter you can keep that time frame, the better the product is going to be in the end. So not getting strung out too far, keeping everything together, obviously with a competent team that can handle it, will always give the best job possible. And then you got some type of a finish rolling on the back end. It could be steel drum, could be pneumatic rollers like this. Sometimes it's a combination of both out there. So it really just depends on local markets, availability, things of that nature. But they all work in their own ways, and they all have their obviously the pros and cons. And then some type of a curing typically could be, like wet cured with water, or you could emulsify cure with emulsion. And, because it's about trapping that moisture in, kind of like your bridge deck. You pour concrete on a bridge deck. What's the best way to cure concrete? Flood it underwater for like a month. So if you can keep it damp, and that you're going to get a better cure out of it. And it's this exact same thing with soils or FDR. If you can keep it damp and like do that, we've had some projects where we treated it and we had some issues with frost maybe coming in and we put the gravel back on top. We actually wet it down when the gravel was sitting right there, and we just laterally moved it over, kept people off of it with loads, and and let that gravel became the actual membrane that trapped the moisture in, and thus then allowed it to help it actually slow cure too. So it just depends on the cost you want to spend. And then there are, obviously regions and things of that nature that it's very common to microcrack. Microcracking happens usually at least 48 to 72 hours, if not longer, after the curing process has happened and the process has been done. And it's basically slightly rubblizing that FDR cross section to create little microcracks in there, and and then those won't reflect through, versus the other stuff, because it's like it still can crack and do that stuff. And that's what I was going to actually bring up a story of. There's something that Don said triggered it. We're doing a project. It's actually a demonstration project up in Fargo, North Dakota, and we did about a half a mile of road for them with all these different cross sections. And I'm walking it with the engineer like a couple of weeks after, and we're walking. We see, just normal cracking, like every 100 feet, you'd see like a hairline crack or something like that. Then all of a sudden the cracks got like 15, 20 feet apart. He's like, "What's going on here?" I said, "I have an idea. I wasn't out here for the last little bit of the job. So I called the foreman on speakerphone. I'm talking to him, and the job required like 35 ton of cement or something like that. It was some odd number. So it was like a partial load. And of course, we ordered what we needed, but what happened, an extra 5 tons showed up. Well, we don't realize the extra 5 tons showed up until after the fact. It's already in the spreader truck. The pneumatic tanker's down the road, and we've already blended in 3/4 of the job. So we got no other place to use the cement. So they just put it on that last little bit of the road. So that last little bit of the road got like a 9% treatment rate instead of a 4 or 5% treatment rate. So it was exponentially stronger than it should have been. And that kind of leads into what Don had, that chart, and and that like that PSI range you want to be, and then you get too strong and more cracking. That's exactly what happened. And it was just it wasn't done intentionally, it was unintentional. And it was just because somebody sent too much material out to the job versus what was ordered. And and we didn't send it back, kind of thing. So it's easy for that kind of stuff to happen. So in a case like that, if it was micro cracked, it might not have had as bad as an effect with like the reflective cracking coming through. So I wanted to share that story. I thought it'd be relevant for the audience. So I think this one's still me, right, Don?
Yep.
So like here, huh?
Yeah, you got this slide, and then I take over after you.
Okay.
Yeah.
So like, obviously then this just shows the surfacing going on here after the fact. You can see curb and gutter, so everything was prepped down lower. I think the picture to the left is actually some projects in Salt Lake City, that were done years ago, and they actually put a concrete overlay on top of those roads. So there's some FDR below that with a cement overlay, actual PCC overlay. And then on the right side, you can see an HMA, overlay going on. I've seen cape seals, I've seen chip seals, I've seen microsurfacing. I've even seen fog seals temporarily go on as an overlay. And that was also another thing I wanted to bring up on the surface things. There's a comment that like Don made about like you can thin up your surface. And I agree, don't turn up, get the life out of the road, but you can also stage that budget. If you got the budget to do it, maybe don't do the surface layer this year. Maybe wait 5 years and do the surface layer because you got plenty of strength below, and maybe do 2 layers of surface instead of just one. And, so if you're going to get, say, 5 inches of HMA, maybe you do 3 inches this year, and then 5 or 7 years when you start to see a little bit of distress in that asphalt, do another overlay with that same exact budget and stretch that budget out longer because you have that strength in the FDR down below. Like one thing we do is a lot of wind farms, and we treat topsoil in wind farms all the time. Thousands of miles a year, of this stuff, and they put 2 inches of gravel on it, 3 inches of gravel on there, and they beat the living what out of it with construction trucks, and it holds up just fine. So like that strength is down below, and that's what that cement is doing. It's giving you that platform to work off of, and it's going to give you that long-term retained strength. And that's the biggest benefit you get out of FDR and soil stabilization, is a retained strength during wet conditions, the non-optimal times. And that is the biggest bang for the buck that you possibly get out of this, in my opinion, is when you have the suboptimal conditions, that 10-15% of the year where it's wet, crappy, this, that, and the other, and every region of the country gets their own version of that. And that's where the best benefit of it comes from. So I think I overdid my talk here for you, Don.
Yeah, thanks, Jonathan. We'll move into the last segment, which is the cement slurry delivered in a ready mix truck. And so just some general comments about the slurries. Of course, they contain cement, water, sometimes chemical admixtures such as a hydration stabilizer that extends the set time. Sometimes water reducers are used. Typically, slurries contain about 70% solids. Remember that the Illinois DOT spec requires 50. So the 70 equates to a water cement ratio of about 0.43. And then trial batches can be run to determine the best water cement ratio with respect to the materials that a given producer has. We put together these charts really for a ready mix producer to provide a starting point, and this would probably be your preferred mix design, everything else being equal, so that you can get the most cement material out to the job site in a ready mix truck. As far as the slurries, once you get out on site, again, the application rate is based on the weight of the cement in the slurry, and the water is just in there to facilitate discharging. Sometimes sand and pea gravel may be added to facilitate the mixing and the placing of it, the flowability. So really, for a given set of materials, a producer should be able to develop one slurry mix design that works best for their materials. And then what varies, so that one slurry design will give you so much cubic or pounds of cement per cubic yard. And based on that, you just change your area that it covers out in the field in order to work with different cement contents. We'll go through an example. As far as charging the mixer, initially, about 80% of the water is added. With the mixer running, the cement is added slowly, then the balance of the water. And generally, you charge only 60 to 80% of the mixer capacity to ensure adequate mixing and minimizing spillage during transport. So you can't utilize the capacities that you would with normal concrete. This is the chart that we looked at earlier. And just as an example, if we were dealing with a soil with a density of 125 pounds per cubic foot, and let's assume we wanted 5% cement, and we're going to treat 9 inches of depth, then using this chart coming over with the 5% coming down at the 9 inches, we would select a spread rate of 42.2 pounds per square yard, or 4.7 pounds per square foot. And it really makes no difference whether that cement is dry or in slurry form. What we're concerned about is the weight of that cement. So for an example, let's say we use that mix design that provides 2,200 pounds per cubic yard, and we got 8 cubic yards of material. We would divide 2,200 times the 8 cubic yards, divide it by that spread rate, and that's going to give us the amount, the 3745 cubic feet. We divide that by, let's say, an 8-foot wide path. Oops, and that tells us that we need 468 linear feet. So the driver of that truck would discharge that entire load at 8-foot wide, 468 foot long. And we'll just look at some of the equipment that's available out here. And you've got a lot of different type of equipment. Here's a modified water tanker that someone put together, and this is a box spreader of some type. So necessity is really the mother of invention in these situations. A lot of times just ready mix chute is used and moved back and forth, and that seems to work fine. You get a lot of mixing with that reclaimer when it comes in and mixes the material. Here you see a spreader that's used in Utah quite a bit. This was invented by a gentleman named John Coyle. I say invented, he fabricated it. He's a city engineer with Salt Lake City, and he developed this in about 2007, and he allowed other cities to use it in Utah. Here you can see a large project. I think this is on I-70 in Indiana, and they're just using the chute itself. And I'll show you just a short clip. So that's a slurry spreader, which is a patented product that a gentleman named Spencer Guthrie has a patent on, and he's building that in Utah. And it's really just an improvement over what John Coyle had originally come up with. Quite a few DOTs do have specifications that allow specifically for slurry. Illinois being the latest one to add that. Just some sample projects, and I won't go over those in detail, but you can see there's a lot of Indiana is using the slurry process on interstate projects. And I suspect that that's in an urban area where they're really concerned about dusting, but they've had very good luck. Kennedy Connector is also a fairly large connector project in the Cincinnati area. And you can see some, again, I-69 north of Indianapolis using the slurry process. I think this was one in Utah, the Kennedy Connector in Ohio, and this is a project that Rock Solid did up in Montana. So it's being used in many parts of the country. And I'll conclude, I'll recommend that if you go to paveahead.com/resources, you can get quite a bit of information on slurries. We have case studies, design and construction publications, and some videos as well if you want to learn more. And here you see quite a few resources, and I would recommend that you reach out to Theron initially, and he can put you in touch with the right resource. He has relationships with all of these various groups and does a great job of getting us involved when the timing is right. And with that, I will return control back to Theron.
Thanks, Don. Great job, Jonathan and Don, with the webinar today. We do have one question that came across, and the question is this being used by IDOT? And I'll start with an answer on that. As of right now, my understanding is no. The special provision just came out, so I'm assuming that IDOT will be looking at different projects that they could now use with the cement slurry process now that they have a special provision for the use of cement slurry. So as of right now, I'm not aware of any projects that IDOT has done, but again, this special provision just came out, so we're hoping to work with IDOT to get some projects going with the cement slurry process.
Yeah, and I was to say, and on just FDR in general with cement, there is the IDOT specifications, and and they use a lot of it, especially in the local roads programs too. So obviously FDR with cement is being used for sure in general.
Yes, thanks, Jonathan, for that clarification. Yeah, the dry powder is being used, but the cement slurry process has not been used yet. With that, I don't see any more questions. Just closing comments. Thank you everyone for tuning in today. Our next webinar is on July 14th at 12 p.m. It is titled Concrete Pavement Myths. We'll be covering such topics as more cement is better, concrete pavements need steel, dowels are needed at all joints, and concrete is more expensive than asphalt. Those are just some of the concrete myths that we'll be covering in the next webinar. Luke McHugh from NRMCA will be the presenter. Registration will open on Monday, June 21st. And as always, IRMCA has all kinds of free engineering assistance for any type of concrete questions that you have from an engineering standpoint or troubleshooting. You can always reach out to NRMCA, and then we work with our partners like NRMCA or Jonathan to help get you answers to those questions. And with that, thanks, John and Don, and I hope everybody has a great rest of the day.
All right. Thank you, Theron.
Thank you.